Thanks, Don. So my name is Jacek Strkowski. I'm a hydrogeologist with Conservation Halton, and I'm going to be talking about wetland hydroperiod and shallow groundwater monitoring program at Conservation Halton. So a quick outline. I'm going to quickly talk about how this program came to be. I'm going to talk about how we instrument our wetlands. I'm going to talk about a bit about, actually mostly about data interpretation and data, about geological settings and wetland relationships, some other key observations and trends, and groundwater and surface water interactions, and then some future considerations and conclusions. So down below we have three pictures of wetlands in Conservation Halton, swamp, marsh, and marsh surrounded by a swamp. So here is Conservation Halton watershed for people who don't know where Conservation Halton is. If you look at the most western tip of our watershed, about 25 kilometers to the west, that's where we are here in this room. You see that the most dominant feature in our watershed is this brown line dissecting our watershed. This is the brow of Niagara Escarpment. And throughout my presentation, I'm going to be talking about wetlands above the escarpment and wetlands below the escarpment. So wetlands above the escarpment will be the wetlands to the west of that brown line, and wetlands below the escarpment will be to the east. You see lots of green blobs. Those are our wetlands. The wetlands above the escarpment usually are larger, but wetlands below the escarpment are probably more numerous, but they are just way smaller. You also see those yellow dots. Those are our instrumented wetlands. So it was about 2011 we started working on a water budget for our source water project with our consultants and municipal partners. We started building a numerical model. We came up with a model domain, and then we found out that 20% of our model domain was covered with wetlands. So I went to our CH staff, our ecology staff, asked for all the hydroperiod data, and I found out that we have none. So fortunately, we had Halton region at the table who were able to provide some equipment, and in 2012 we instrumented first 5 wetlands. And since then the program expanded. We have right now 10 long-term monitoring wetlands. So in terms of instrumentation, all our wetlands have either 1 or 2 instruments. So if there is only 1, it's a drive point which is designed to basically monitor wetland hydroperiod. If there are 2, the other one is designed to monitor shallow groundwater. And by shallow, I mean really shallow. So the top of the screen of the drive point would be usually between 0.9 to 1.8 meters. Those drive point piezometers are simply equipped with data logging transducers, which after download we compensate the data for barometric pressure changes. When we are out there, we monitor manual water levels on the inside and on the outside of the drive point piezometers for reference. So here are 4 examples of our actually instrumented wetlands. The one on top is Futurelli. It's a marsh. It's got 2 instruments. Then to the right, you've got the Crawford Lake. It's a vernal pool, and it's got 1 instrument. We've got a swamp at Moundsburg. Again, has 2 instruments, and another marsh in North Oakville with 2 instruments. So as I said, we started monitoring wetlands in 2012. So we've got 12 or over 12 years of data for at least 5 of the wetlands. And every year we keep adding more data, and our graphs get squished, and it's more difficult to see where the hydroperiod starts, where it ends. And in this graph, we've got shallow groundwater monitor and wetland hydroperiod monitor. So the red dots are basically the surface water level. The blue dots are shallow groundwater levels. What's interesting in this graph is that blue dots quite often are above the red dots, which means shallow groundwater is actually higher head than surface water level, which suggests that there is some potential for groundwater discharge in this wetland. So these graphs obviously are very valuable. You can see some drought scenarios. For example, 2022, there's a big dip, and there is another one in 2016. And you can see in 2012, like the beginning of the hydrograph, that was also drought year. When we instrumented the wetland, it was just the tail end of the drought year. So here is an example of another hydrograph. So different geologic conditions. I talked about wetlands above the escarpment, totally different geology than wetlands below the escarpment. Below the escarpment, we've got clays over shales. Above the escarpment, we are dealing with dolostone bedrock, either Gosport, Ramosa, or we've got a bit of Guelph. And there is obviously some clays or some outwash sands above it. Again, but it's difficult, it gets messy, it's really difficult to try to find out what are the beginnings and ends of the hydroperiod in the wetlands. So we started doing these graphs, composite graphs or spaghetti graphs, whatever you call them. So we are plotting all the 12 or 13 years of data on one graph using same axis. And right away you can see that, right away you can tell when the wetland had standing water. So for the first few months, for example, you can see that the wetland always, over the 12-year period, had always standing water. If it wasn't for this year, which is 2022 drought, the wetland also had standing water in November and December. So right away you can see more. You can see all three drought years, 2012, 2016 to 2022. Here is another example, different wetlands. This one is North Oakville, different geologic conditions, clay at surface. And again, you can see when the wetland is always dry, at least over the monitoring period, or when it always had standing water, like this. Oops, sorry. So this had standing water over the 11 years, only a month and a half. The previous one had standing water for 9 months or so. Again, but it's kind of messy. So there is another example. This is a vernal pool, lots of standing water, and it dries up sometimes. But again, quite messy. So we basically decided to step away from those spaghetti or composite graphs and to basically show minimum, maximum water levels over the monitoring period and just do some basic statistical analysis to show basically percentile water level. So we are showing 10 percentile, 25 percentile, median, 75 and 90 percentile water levels. So all the water levels measured over the 12 or 13-year period basically would fit in between those lines. So here is an example of that another wetland in North Oakville. Again, different geologic conditions. This wetland dries up quite often. And this is an example of our vernal pool at Hilton Falls. Again, lots of water. And what we are going to concentrate on from now on in this presentation is basically the median water levels. So this is the green thick line in between. So here is basically a graph of all the median water levels for all our wetlands with at least 5 years of monitoring data. And we are trying to find out if there are any similarities between the wetland responses. Right away you can see that two of them stand out, CL1 and HF1. And the good thing is they are both similar type of wetlands. So they are vernal pools surrounded by sugar maple swamps. You see that these wetlands, they've got very long hydroperiod, and they do dry up on average for just a couple of months of a year. So here are all the remaining wetlands. I've got lots of slides, so I have to skip over some of them. Anyway, so here we've got wetlands which are above the Niagara escarpment, just to see if there are any similarities. Wetlands below the escarpment, you see that the response here is a bit different. Again, different geologic conditions, lots of clay at surface. The wetlands don't get as much water, and they do dry up quicker, and the shallow groundwater levels do actually drop down a bit deeper. So for all the wetlands above the escarpment, some of the similarities is that some of the wetlands have very shallow bedrock. Usually it's Gosport. And here I'm presenting basically hydrologic responses, median water levels, again, for wetlands with shallow bedrock. You can either see it from wherever the installation is, or you can definitely trip over it on the way to the wetland. And here are responses of all the wetlands which have clay till or glacial lacustrine clay at surface. So 3 of these are actually below the escarpment, and 2 of them are above the escarpment. And I'm not sure if you can see. Yeah, I think you can see it. So 3 of them are those 3 are below the escarpment. They dry up quicker. The green one is actually, it has clay at surface. It is above the escarpment, and we don't know how deep the bedrock is. It's in the middle of a woodlot, so there are no water well records or anything like that to tell us how thick the clay is. It's kind of similar response to the ones below the escarpment. One of them stands out completely, so it's this one. So this one is also above the escarpment. It has clay at surface, about a couple meters of clay. Then it's probably 8 to 10, based on water records in the area, about 8 to 10 meters of sand over the Yellowstone bedrock. This wetland is different because it has documented upward gradients. So for all the wetlands, when we've got at least 2 instruments, we did calculate the vertical gradients just to see if there is any potential for groundwater discharge into the wetlands. So here is an example of Mounsberg wetland. So you see that most of the time it actually has upward gradient. So there is a potential for groundwater discharge. And here are all the wetlands which actually have documented upward gradients. Maybe it's not as dominant as the Mounsberg, but they definitely receive some potentially groundwater discharge. You see these wetlands, they don't really fluctuate as much. Like you see that the annual fluctuations are probably within half a meter or less. And so here are vertical gradients, 0 gradient to downward gradient mostly, and here are all the wetlands which have 0 gradients or downward gradients. So again, all the 3 wetlands below the escarpment and the one on top of the escarpment, which also has clayed surface, shows the similar response. So in terms of wetland types and hydrologic responses, here I'm showing all the wetlands, all the marshes which we have instrumented. You see that one of them stands out, and there is a reason for it. This marsh is actually riparian marsh, so there is some local water course which definitely influences the hydro period. The other 2 are definitely headwater marshes. And here are our swamps. I'm not showing Crawford Lake, the HF1 and CL1, the ones which really stood out. Also, they are all vernal pools surrounded by swamps. But these swamps are, so we've got 3 swamps showing, and one of them is below the escarpment. Right away, it stands out or stands down. It's below the escarpment. The other 2 are above the escarpment. Both of them receive groundwater discharge. Some monitoring challenges, obvious. All our sites are manual, so we have to be actually out there to collect the data. Bugs, sometimes like the picture in below, like if there are some 2 pipes in the middle of those cattails, it's not easy to find, even if you know where they are. There are some other monitoring challenges. For example, after a few years, in one of our wetlands, we were starting getting this drift, and nothing made sense. All the manual water levels supported that there is a drift. So the reason for the drift is, like the left picture shows the installation right after it was put in place, and the other one is 4 years later. So one of our drive points, which originally was about 25 centimeters higher than the other one, was basically driven most likely by an ice sheet over the winter time, and so after 4 years actually was lower by some 30 centimeters than originally put in. So we've got really soft organic muck, and so maybe it sank under its own weight. And just quickly, so similarly to those water level envelopes, we developed groundwater envelopes for our PGMN wells. And the reason for this is that we are considering including groundwater level indicator on our website, similarly to what we have for flood and low water risk. So basically, we would be looking on a monthly basis, looking at the last 30 days of groundwater level data, and we would be plotting it on our water level envelope on the spectrum, and right away we would be able to say where we are. For example, this is 2007 data. It was a drought year, so this data actually stretched our groundwater level envelope. And here are some examples how we would basically say, okay, this is normal or lower, normal, above normal, or extremely high water level, groundwater level. Just interesting response, 2024, it was a wet year in Conservation Halton, recharge happening, like what Mason showed, some of the spikes. This well also responds very well to precipitation event, and we got this huge spike in July when we received a lot of precipitation, which caused this huge spike in the middle of our groundwater envelope. Same weather event in one of our wetlands, highest water levels over 12 years of monitoring in July. Kind of unusual. Usually it's in the springtime during spring freshet. So we would like to continue the program. We would like to expand if it's possible. We want to spend definitely more time looking at the ELC data with our ecologists to come up with some representative species. This work is ongoing. And some conclusions, wetland hydrology is highly dependent on geologic setting. Groundwater is very important for wetlands. Proper placement of instruments is very important. And obviously you need continuous multi-year data to come up with any conclusions. And development planning must consider groundwater when we are dealing with wetlands. And the wetland replication should match natural hydrologic conditions to support the wetland species. And huge thanks to Halton Region, John, Benham, and Tom for providing the equipment, physically helping, always supporting the program, Holly, Tanya, and Lisa, our ecologist, and a number of people who helped over the 12 years of monitoring with the program. Thank you.